Hey guys, welcome back. This is going to be part B of lesson 3.5, Shapes of Graphs. And the two things we're going to talk about here today will be the extrema values, which we did not cover in any detail in the first video, and determining the end behavior of graphs of functions. We're also going to define relative and min and max values, and of course the end behavior that was already defined for you in the first video. We are going to use the Desmos calculator to describe most of what we're doing here. Okay, so the first thing I want to do is define for you what relative min and max values are. When a graph changes from decreasing back to increasing, we learned that in the first video, so the y values are getting smaller, then they go back to bigger. At the point of inflection where that occurs, that's called a relative minimum. When the graph changes from increasing back to decreasing, at that point of inflection, we call that the relative maximum. So take a look at the graph here. I've got that cubic from the first one, and I've got that line that's tracing it. So as we're moving from left to right, you'll notice the y values are getting smaller, little at a time. And eventually they hit this low part, and then they start to go back up. When we had that direction change from decreasing back to increasing, right in the middle there, that was our relative minimum. Now Desmos has this nice feature in which we can actually just click on the graph and it can tell us what the relative min or max value is. So our extrema values are going to be obviously right here and over here. But the one on the left, we call this one a relative minimum, and this one we call it a relative maximum. One other very key feature here that we talk about min and max values. Min and max are output values. That means when we're asking for the min or max value, we're talking about the y coordinate at the min or max. So down here, the relative minimum is negative 7.065. Even though the domain value of negative 1.869 causes that to happen, the actual min or max value is always the output. In other words, it's the y value. So we can see that we have a relative minimum at negative 7.065. Now these are actually irrational numbers, so we're just going to estimate them to 2 to 3 decimal places. So I'm going to turn that one off. And then as we run this through, so we have this graph is increasing, y values are getting bigger, then all of a sudden the y values get smaller on the other side of that curve. So they get bigger left to right, and then they get smaller. And what happened there was we went through a relative maximum. So I'll move this line out of the way. Again, Desmos has the ability to tell us what that relative maximum is. And remember that relative min and max values are always the output values. So out of the two numbers you see there, the negative 0.121 is the relative max. Okay, so over here on example 4, they want us to determine the extrema of the graph of the function. Determine the extrema of f of x. Identify each point as relative max or relative min. Okay, so extrema points are the points where it changes from increasing to decreasing or from decreasing back to increasing. So we can clearly see on the graph we have this point here and we have this point here. So that's point B and point C. Are locations of relatively high or low values, so they are the extrema of the function. Relative minimum, no other points nearby point C have a lesser y coordinate, so point C is the relative min, and the relative maximum, no other points nearby point B have a greater y coordinate, so point B is a relative maximum. Go ahead and pause the video and attempt the check. For this check, it wants to know which points are relative minimum. They are saying minimum. Select all that apply. So on the graph, minimum is where the graph changes from decreasing back to increasing. Wherever that happens, that's a relative minimum. Well, on our graph, we can see it happens here at point B, and then again over here at point D. So the choices are B and D. A comic book store uses a function to model its profit in thousands of dollars given the price in dollars that it charges for individual uses, determine whether point D is a relative minimum, relative maximum, or neither. Then interpret its meaning in the context of the situation. Well, if you look at point D, which is up here at the top, you can see on the left-hand side of that point, the Y values are increasing. On the right-hand side, the Y values are decreasing. So when we go from increase back to decrease, we call that a max. So point D is a maximum. And I think they wanted me to put relative maximum there because all nearby points have a lesser Y value. So all the points on this side are smaller and all the points on this side are smaller. So point D represents the biggest profit or maximum profit. Let's go with max profit that the comic book store can earn given the price it charges per issue. Go ahead and pause the video and attempt the check here. Okay, so we've got aerobatics or stunt flying, the practice of intentional maneuvers on an aircraft that are not necessary to normal flight. Lincoln Beechey, an inventor of aerobatics, was known for his stunt called the Dip of Death, in which his plane would plummet toward the ground from 5,000 feet until he leveled the plane. His distance from the ground during the stunt can be approximately modeled by the function f of x. Identify any extrema in the content of the situation. Okay, it looks like right here he's reached his maximum altitude because on the left-hand side our altitude is still going up. And on the right-hand side, the altitude is going down, so that's the definition of a maximum. So point A represents that at about 20 seconds, Lincoln Beechey reached a maximum in height at 5,000 feet. After point A, his height is decreasing until he levels out the plane. Okay, for this next part, we're going to talk about the end behavior, and you can see the definition of end behavior there again. But I am going to describe this on the Desmos calculator. So let's go back to the Desmos calculator. Okay, so here we have a cubic again. So up here we have an arrow going that direction forever. And on the bottom right, we have an arrow going that direction forever. So end behavior. Here's what end behavior means. If you went to the right forever, so your x values are going towards positive infinity, you keep going infinitely to the right. The question then is, what's happening to the y values? What are they doing as we infinitely go to the right? So if I trace this and I infinitely go to the right, and I keep going to the right, and that's where that arrowhead down here tells me it's going towards negative infinity. So the y values are going to approach negative infinity. Now, the different ways that we can state this is, as x increases, y decreases. So that is the end behavior on the right side of the graph. Now we got to describe the end behavior on the left-hand side of the graph. So now as x goes infinitely to the left, or in other words, as x decreases, what does y do? So as we trace this and we go left and we keep going left and we keep going left, well, the y values are all going to go up, so that would be increases. So now we have the behavior on the left side of the graph. Now, what's another way that we can express this? This is the simpler way. So as x increases, y decreases is the right side behavior. And as x decreases, y increases the left-hand behavior or end behavior. So another way to express this, the right-hand behavior would be as x approaches infinity, and that little arrow pointing to the right means approaches, then its output, which is called f of x, remember that replaces the y value, approaches negative infinity. So it's pointing down. So this is pointing to the right, and this arrow says it's going to be pointing down as you go to the right. That's the right-hand behavior. The left-hand behavior would be as x approaches negative infinity. Negative infinity is to the left. That means as the graph goes towards the left, the output values, or f of x, will approach. They keep going up, which is positive infinity. So that would be up. So this is the left-hand behavior in a more advanced form, and this is the right-hand behavior in a more advanced form. For example 6, they want us to determine end behavior of the graph of a linear function. So this says as we move to the left on the graph, so we're going in this direction, what is happening to y? As we go down this line, it's going, the y values are getting smaller. So the value of y gets increasingly smaller. Thus, as x decreases, y decreases. As you move to the right, so as the graph goes to the right, the x's are getting bigger. The y values along this line will get increasingly larger. Thus, as x, and they said this wrong, this should be increases, y increases. And if we showed that with our other form, we would say as x approaches infinity, that's going to the right, f of x approaches positive infinity also. So this is the right-hand behavior. And the left-hand behavior, as x approaches negative infinity, because on the number line to the left is negative infinity for x, then f of x approaches negative infinity also. Go ahead and pause the video and attempt the check. Okay, for this one, we're still going to determine the end behavior of f of x, and it's still another linear equation. So the first part says as x increases, so x increasing is in this direction. The graph then is going up forever, so y is increasing. So as x increases, y increases. As x decreases, meaning x is going to the left towards negative infinity, y then is going to go downwards towards negative infinity, which would be a decrease. For example 7, we're going to determine the end behavior of the graph of a nonlinear function. So you can see we have a cubic over here. As you move to the left on the graph, the values of y gets increasingly, so left is this direction. Now if we look at the arrow on the left-hand side, it's pointing down. That means our y's are going to get increasingly smaller. Thus, as x decreases, y decreases. As you move to the right on the graph, that means we're going in this direction, to the right. Y gets increasingly, if you follow the arrowhead here, it's going up towards positive infinity. So y gets increasingly larger. Thus, as x increases, y increases. Okay, so this first part here said to the left, so that's left-hand behavior. And the second part said to the right, that's right-hand behavior. So when you're ever asked for end behavior of a function, we have two behaviors. We have left-hand behavior and right-hand behavior. Go ahead and pause the video and attempt the check. Okay, for the check, we're going to determine the end behavior of each function. So as x increases on this first one, x increases on the first one, x is going this way. The arrow is pointing up in that direction, so y will also increase. And as x decreases, meaning x is going in this direction, we look at the arrow on that side, it is also increasing. And you'll notice on both of these end behaviors, the y values are increasing. That's because both arrows were pointing upwards. The second part of the check, as x increases, so as x goes infinitely to the right, the y values appear to go up. That's the direction of the arrow, so y increases. And as x decreases, meaning x goes to the left towards negative infinity, the y values will increase, which is going up on that arrow side. So as x increases, y increases. As x decreases, y still increases. So the first one up here is right-hand behavior, and the second one is left-hand behavior. And the way you can tell the behavior is to look at the value of the x. X is increasing, which goes to the right. The second one, x decreases, which goes to the left. And that's the difference between right and left-hand behavior.